Welcome to DAR Tutors. We provide expert tuition in IB, A-Level, and IGCSE curricula. Today, we will be focusing on the fundamental principles of stoichiometry and the mole concept, which are essential for IB chemistry higher level. By the end of this session, you will be able to perform stoichiometric calculations involving mass, moles, and gas volumes, determine empirical and molecular formulas, calculate percentage composition, and apply these concepts to experimental techniques like titrations and gravimetric analysis, while also understanding the propagation of uncertainties. Our first topic is determining the masses of products in a reaction using stoichiometry. Chemical equations provide us with crucial information. They can be interpreted in three main ways: by the number of molecules, by the amount in moles, and by the mass in grams. The coefficients in a balanced equation represent the ratios in which reactants and products participate. Let's take the classic Haber process as our example. Nitrogen reacting with hydrogen to form ammonia. In terms of molecules, this equation tells us that one molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. This ratio holds true regardless of the number of molecules. For instance, 100 molecules of nitrogen would react with 300 molecules of hydrogen to produce 200 molecules of ammonia. This concept extends to moles. 1 mole of nitrogen reacts with 3 moles of hydrogen to form 2 moles of ammonia. This mole ratio is the cornerstone of all stoichiometric calculations. To relate moles to mass, we use the molar mass. The molar mass of N2 is 28.02 gr/mol. For H2, it's 2.02 gr/mol, and for NH3, it's 1704 gr/mol. So we can say that 2802 grams of nitrogen reacts with 3 times 2.02, or 6.06 grams of hydrogen, to yield 2 times 17.04, or 34.08 grams of ammonia. Notice that the total mass of the reactants, 28.02 plus 6.06, equals 34.08, which is the mass of the product. This demonstrates the law of conservation of mass. Solving stoichiometry problems involves a systematic 4-step process. First, always ensure you have a balanced chemical equation. Second, convert the mass of the known reactant or product into moles using its molar mass. Third, use the mole ratio from the balanced equation to find the moles of the substance you need to calculate. Finally, convert those moles back into a mass. Let's work through an example. What mass of water is formed when 8.08 grams of hydrogen gas reacts with an excess of oxygen? Step 1 is to write the balanced equation. Hydrogen plus oxygen gives water, which balances to 2H2 plus O2 yields 2H2O. So 2H2 plus O2 yields 2H2O. Step 2 is to convert the mass of hydrogen to moles. The molar mass of H2 is 2.02 gr/mol. We divide the mass, 8.08 grams, by the molar mass. 808 grams divided by 2.02 grams per mole gives us 4 moles of hydrogen. Step 3 involves the mole ratio. From the balanced equation, we see that 2 moles of hydrogen react to form 2 moles of water. This is a 1-to-1 mole ratio. Since the ratio of H2 to H2O is 2-to-2, or 1-to-1, 4 moles of H2 will produce 4 moles of H2O. Finally, step 4, we convert the moles of water to grams. The molar mass of H2O is 18.02 gr/mol. We multiply the moles of water, 4 by its molar mass, 18.02 gr/mol, to get our final answer, 72.08 grams of water. Always include units in your final answer. It's important to understand a common misconception. The coefficients in a balanced equation do not directly represent the number of atoms of the elements in the substance. Instead, they represent the ratios of the numbers of atoms, ions, molecules, formula units, or electrons that are involved in the chemical reaction. They tell us the relative amounts, not the internal composition of a single substance. Let's work through another stoichiometry example involving a real-world application. Sulfur dioxide is a pollutant. It can be removed from the air using calcium carbonate. The question asks what mass of calcium carbonate is needed to remove 1,000 grams of sulfur dioxide. First, we confirm the equation is balanced. We have 2 calcium atoms on both sides, 2 sulfur atoms, and on the left, 6 oxygens from calcium carbonate plus 4 from sulfur dioxide plus 2 from oxygen, making 12 oxygens. On the right, we have 8 from calcium sulfate plus 4 from carbon dioxide, also 12. The equation is balanced. Next, we find the molar mass of sulfur dioxide. Sulfur is 32.07 and oxygen is 1600. So the molar mass of SO2 is 32.07 plus 2 times 1600, which equals 64.07 g/mol. Now we convert the mass of SO2 to moles. 1000 grams divided by 64.07 grams per mole gives us 0.1061 moles of SO2. Looking at the balanced equation, we see that 2 moles of KCO3 are needed for every 2 moles of SO2. This is a 1-to-1 ratio. Therefore, if we need to remove 0.561 moles of SO2, we must use 0.561 moles of KCO3. The final step is to convert moles of KCO3 to mass. The molar mass of KCO3 is 40.08 for calcium, 12.01 for carbon, and 3 times 1600 for oxygen, totaling 100.09 g/mol. We multiply the moles of KCO3 by its molar mass to get our final answer, 15.62 grams. So, 15.62 grams of calcium carbonate are required to remove 10 grams of sulfur dioxide. Next, we will explore the concepts of molecular and empirical formulas. The molecular formula shows the actual number of atoms of each element in a molecule. The empirical formula, on the other hand, shows the simplest whole number ratio of atoms in a compound. Let's look at an example. The molecule propene has the molecular formula C3H6. The simplest whole number ratio of carbon to hydrogen is 1 to 2. Therefore, its empirical formula is CH2. Propane, with a molecular formula of C3H8, already has the simplest ratio of 3 to 8, so its empirical formula is the same, C3H8. As you can see, the molecular formula provides a complete picture of the molecule's composition, while the empirical formula gives a basic ratio-based description. It's important to note that many different compounds can share the same empirical formula. For example, CH2 is the empirical formula for ethene, C2H4, propene, C3H6, and cyclobutane, C4H8. For ionic compounds like N-acly or CaO, or giant molecular structures like SiO2, the empirical formula is the only chemically meaningful formula. This is because these structures are not composed of discrete molecules, but rather an infinite lattice of ions or atoms in a fixed ratio. A key skill in chemistry is calculating percentage composition by mass. This tells you the percentage of each element's mass relative to the total mass of the compound. The general formula is the mass of the element divided by the molar mass of the compound, all multiplied by 100%. Let's calculate the percentage composition of nitrogen and oxygen in nitrogen 3 oxide, N2O3. First, we find the molar mass of N2O3. It has 2 nitrogens, each 14.01 g/mol, and 3 oxygens, each 1600 g/mol. The total molar mass is 28.02 plus 48, which equals 76.02 g/mol. Now, let's calculate the percentage of nitrogen. The mass of nitrogen in 1 mole of N2O3 is 28.02 grams. So, we divide 28.02 by the total molar mass, 76.02, and multiply by 100%. This gives us 36.86% nitrogen. Next, for oxygen, the mass in 1 mole is 4,800 grams. Dividing 4,800 by 76.02 and multiplying by 100% gives 63.14% oxygen. To check our work, we can sum the percentages. 36.86 plus 63.14 equals 100%, so our calculation is correct. Remember, always check your work. We can reverse this process to determine an empirical formula from mass data. This is a common laboratory procedure. The steps are: first, write down the mass of each element. Second, convert the mass of each element to moles. Third, divide each mole value by the smallest number of moles to find the simplest ratio. Fourth, express this as a whole number ratio, multiplying if necessary. Finally, write the empirical formula. Let's apply this to a sample of a lead-sulfur-oxygen compound. Determine the empirical formula for a compound with 8.32 G lead, P1.28 G sulfur S, and 2.56 g and oxygen O. We are given the masses. Pb is 8.32 g, S is 1.28 g, and O is 2.56 g. First, convert each to moles. Lead, 8.32 divided by its molar mass, 207.2 g, gives 0.402 moles. Sulfur, 1.28 divided by 32.07 gives 0.0399 moles. Oxygen, 2.56 divided by 16 gives 0.146 moles. Now we find the simplest ratio by dividing by the smallest mole value, which is 0.0399 moles for sulfur. For lead, 402 divided by 0.0399 is approximately 1.008, which we round to 1. For sulfur, it's exactly 1. For oxygen, 0.160 divided by 0.0399 is approximately 4.010, which we round to 4. Our whole number ratio is 1.14. Therefore, the empirical formula of the compound is PbSO4. This is an excellent example of how we use experimental mass data to deduce the chemical composition of a substance. There are some important considerations when conducting experiments to determine empirical formulas. These experiments are susceptible to errors. We can categorize errors as either systematic or random. Systematic errors are flaws in the methodology, apparatus, or instrumentation, leading to inaccurate results that are consistently higher or lower than the true value. For example, a balance that is not calibrated correctly will give systematic errors. These errors can often be detected by using a different method or apparatus. Random uncertainty, on the other hand, is always present and cannot be fully corrected. It arises from the precision limitations of repeated measurements and causes results to scatter around the true value. For example, the last digit on a digital balance display has an associated random uncertainty. To account for this, we take multiple measurements and calculate an average. Let's work through an IB-style problem that requires us to deduce the identity of an unknown metal. The problem states that a metal, M, forms an oxide with the formula MO, and this oxide contains 39.70% oxygen by mass. We need to identify M. A key strategy here is to assume a 100-gram sample of the compound. If it's 100 grams, then 39.70% of it is just 39.70 grams. The rest of the mass must be the metal M, so the mass of M is 100 minus 3970, which is 6030 grams. So our 100-gram sample contains 3970 grams of oxygen and 6030 grams of metal. Now we convert the mass of oxygen to moles. Moles of O equals 39.70 grams divided by 1600 grams per mole, which is 2.481 moles. The formula MO tells us there's a 1-to-1 mole ratio between M and O. Therefore, if we have 2.481 moles of O, we must also have 2.481 moles of M. To identify the metal, we need to find its molar mass. Molar mass is mass divided by moles. We divide the mass of the metal we calculated, 60.30 grams, by the moles of the metal, 2.481 moles. This gives a molar mass of 24.31 grams per mole. By looking up this value on the periodic table, we find that the relative atomic mass of magnesium is 24.31. Thus, the metal M is magnesium. So, by combining percentage composition and mole calculations, we can successfully identify unknown elements in a compound. Now, let's bridge the gap between an empirical formula and a molecular formula. The molecular formula is always a simple whole number multiple of the empirical formula. We find this multiple N by dividing the molecular formula mass by the empirical formula mass. Let's work through an example where we are given the empirical formula, but need to find the molecular formula. Worked example. An iron-containing protein has a molar mass of 136,000 g/moles. It is 0.3% iron by mass. Calculate the number of iron atoms per molecule of the protein. This problem doesn't give us the empirical formula directly, but we can deduce it. We need to find the number of iron atoms in one molecule of the protein. First, let's determine the mass of iron in 1 mole of the protein. 1 mole of the protein weighs 136,000 grams. Since 0.33% of this mass is iron, We multiply the molar mass by 0.0033. This gives us 448.8 grams of iron per mole of protein. Next, we convert this mass of iron into moles of iron. We divide the mass by the molar mass of iron, which is 55.85 g/mole. So 448.8 grams divided by 55.85 grams per mole gives us 8.03 moles of iron. Since a molecule must have a whole number of atoms, we round this to 8 moles of iron. This result tells us that 1 mole of the protein contains 8 moles of iron atoms. Therefore, 1 molecule of the protein contains 8 iron atoms. This highlights a powerful application of these calculations, determining the precise composition of very complex molecules like proteins. A hydrated salt is an ionic salt that contains water molecules chemically bonded within its crystal lattice. This is known as water of crystallization. These compounds have a specific formula, like MgSO4.XH2O, where X is a whole number indicating the number of water molecules per formula unit of the anhydrous salt. An anhydrous salt is the form without any water. We can determine the value of X experimentally by heating the hydrated salt to remove the water. The experimental technique is called drying to constant mass. In this method, you heat the sample in a crucible and periodically measure its mass. When the mass no longer changes between readings, it means all the water has been driven off. This ensures you have the mass of the anhydrous salt. Here we see the dramatic color change that often occurs when water of crystallization is removed. Blue hydrated copper 2 sulfate turns into white anhydrous copper 2 sulfate. Let's work through an example to calculate the formula of a hydrated salt. We have the data from heating hydrated cobalt 2 chloride. We need to find the formula CoCl2.XH2O. First, we need to find the mass of the hydrated salt, the anhydrous salt, and the water lost. The mass of the hydrated salt is the total mass minus the crucible mass, which is 2.38 grams. The mass of the anhydrous salt is the final mass minus the crucible, 1.30 grams. The mass of water lost is the difference, 1.08 grams. Now we need to find the mole ratio of the anhydrous salt to the water. The molar mass of CoCl2 is 129.83 g/mole. So 130 grams divided by this gives 0.01 moles of CoCl2. The molar mass of water is 18.02 g/moles. 1.08 grams divided by this gives 0.0599 moles of H2O. To find X, we find the mole ratio of water to the anhydrous salt. X is 0.05910 divided by 0.0100, which is approximately 6. Therefore, the formula of the hydrated salt is CoCl2.6H2O. Note that the significant figures were rounded at the end. Gravimetric analysis is a powerful analytical technique for determining composition based on accurate mass measurements. It's often used to deduce the equation of an unknown reaction. Let's work through an example where we deduce a chemical equation from experimental mass data. In this experiment, 2.431 grams of magnesium react with 1.600 grams of oxygen to form 4.031 grams of magnesium oxide. We can deduce the equation. Our goal is to find the simplest mole ratio of the reactants and products. We'll follow a similar process to finding an empirical formula. First, we calculate the moles of each substance. For magnesium, 2.431 grams divided by its molar mass, 24.31 gigauss-mole, gives 0.1000 moles. For oxygen gas, O2, the molar mass is 3200 mole, so 1.600 grams divided by 3200 gives 0.05 thousand moles. And for magnesium oxide, MgO, the molar mass is 40.31 g/mole, 4.031 grams divided by 40.31 gives 0.1000 moles. The next step is to find the simplest whole number ratio by dividing each mole value by the smallest, which is 0.050 moles. 0.1000 divided by 0.05000 is 2. 0.05000 divided by 0.05 is 1. And 0.1000 divided by 0.05 is 2. The reacting mole ratio is 2.12. We use these whole numbers as our coefficients to deduce the balanced chemical equation. 2 molecules plus O2 yields 2 O. Molar concentration is a measure of the amount of solute, in moles, dissolved in 1 cubic decimeter of solution. It's often represented by the symbol M or by square brackets, like H2SO4AQ. The fundamental formula relating moles, concentration, and volume is moles equals concentration times volume, where the volume must be in cubic decimeters. Remember to always use volume in cubic decimeters, which means dividing any volume in cubic centimeters by 1,000. Let's calculate the mass of potassium hydroxide in a specific volume and concentration of solution. First, we convert the volume to cubic decimeters. 2500 cm3 is 0.2500 dm3. Next, we calculate the moles of KOH. We multiply the volume in dm3 by the concentration. 0.02500 dm3 times 0.125. Mole dm3 equals 0.031225 moles of KOH. Finally, we convert moles to mass. The molar mass of KOH is 39.10 plus 1600 plus 1.01, which is 56.11 g/mole. We multiply the moles of KOH by its molar mass to get our final answer, 0.1754 grams. So, 0.1754 grams of KOH are dissolved in this solution. It's also crucial to remember that for ionic solids, the concentration of the individual ions might be different. For example, if we have a 0.1 m MgCl2 solution, it dissociates to form 0.1 m Mg2 plus ions and 0.2 m Cl ions, because each formula unit produces 2 chloride ions. Titrations are a fundamental experimental technique used to determine the unknown concentration of a solution. This is achieved by reacting it with a solution of accurately known concentration, called a standard solution. A standard solution is made by dissolving a precisely measured mass of a primary standard into a precise volume. A primary standard must be a substance of high purity and stability, with a relatively high molar mass to minimize weighing errors. Here we see the equipment for an acid-base titration. A burette is used to deliver an accurately measured volume of one solution, called the titrant, into a conical flask. The flask contains a known volume of the other solution, measured with a pipette and a few drops of an indicator. The titration continues until the indicator changes color. This point is called the endpoint, which is a visual sign that the reaction is complete. Ideally, the endpoint should be as close as possible to the equivalence point, the point where the reactants are in their exact stoichiometric ratio. Let's work through an example where we need to deduce the balanced equation from titration data. Here we titrate phosphoric V acid with potassium hydroxide. We need to find the mole ratio of H3PO4 to KOH. First, calculate the moles of H3PO4. Moles equals concentration times volume. The volume is 0.102,000 dm3, so 0.0656 mole dm3 times 0.02,000 dm3 gives 0.00132 moles of phosphoric acid. Now for KOH, moles equals 0.150 mole dm3 times 0.0175 dm3, which is 0.02625 moles. To find the whole number ratio, we divide by the smaller mole value, which is 0.013 moles. The mole ratio for H3PO4 is 0.00131 U divided by itself, which is 1. The mole ratio for KOH is 0.002x25 divided by 0.01312, which is approximately 2. So the mole ratio is 1 to 2. This means that 1 molecule of phosphoric acid reacts with 2 molecules of potassium hydroxide. The equation is H3PO4 plus 2 KOH yields K2 to HPO4 plus 2 H2O. Notice that only 2 of the 3 acidic hydrogens were neutralized, which is possible for polyprotic acids. In IB chemistry, you must be able to express, record, and propagate uncertainties in your measurements. Every measurement has an associated uncertainty, which can be absolute, fractional, or percentage. The absolute uncertainty, dx, is the range in which the true value likely lies. Fractional uncertainty is the absolute uncertainty divided by the measurement itself. Percentage uncertainty is the fractional uncertainty multiplied by 100. When you perform calculations using multiple measurements, you must propagate or combine their uncertainties. For addition and subtraction, you add the absolute uncertainties. For multiplication and division, you add the percentage uncertainties. It's crucial to understand the difference and apply the correct rule. Let's work through a detailed titration example that includes calculating and propagating uncertainties. This problem describes a titration to find the molar mass of an unknown acid. We have the mass of the acid and the concentration of the sodium hydroxide standard. We also have titration data. The first step is to process the raw titration data. The volumes delivered are 25.60, 2540, and 2545. We discard the first reading, 2560, as a trial. We take the mean of the two concordant results, 2540 and 2545. The average is 2543 cm3. The uncertainty in a burette reading is plus 0.005 cm3. Since we take two readings, an initial and a final, the absolute uncertainty in the volume delivered is 2 times 0.05, which is plus 0.10 cm3. Now for the error propagation. This will be a multi-step process. Step 1. Convert all given absolute uncertainties to percentage uncertainties. For example, the percentage uncertainty in the mass of the acid is 0.02 divided by 2.355 times 100, which is 0.08%. We do this for the volumetric flask, pipette, and NaOH concentration. The percentage uncertainty in the mass is 0.08%. In the volumetric flask, it's 0.12%. In the pipette, it's 0.30%. And in the NaOH concentration, it's a significant 5.0%. Step 2. Calculate the moles of NaOH used. Moles equals concentration times volume. So moles of NaOH are 0.2543 dm3 times 0.100 mol dm3, which is 0.02543 moles. Now propagate the uncertainty for this multiplication. We add the percentage uncertainties of concentration and volume. The percentage uncertainty for the NaOH volume is 0.1 divided by 25.43 times 100, which is 0.39%. The total percentage uncertainty in the moles of NaOH is 5.0% plus 0.39%, totaling 5.39%. We then convert this back to an absolute uncertainty. Step 3. Calculate the moles of the acid in the 2000 cm3 sample. Since the acid is monoprotic, the mole ratio of acid to base is 1.1. So the moles of acid are the same as the moles of NaOH, 0.2543 moles. Step 4. Calculate the concentration of the acid. Concentration equals moles divided by volume of the acid sample. The volume of the acid from the pipette is 2000 cm3, or 0.02 dm3, so the concentration is 0.127 mol dm3. Again, we propagate uncertainty. We add the percentage uncertainties for moles of NaOH and the volume from the pipette. The percentage uncertainty is 5.39% plus 0.13, which is 5.69%. We convert this to an absolute uncertainty to get plus 0.0072 mol dm3. Step 5. Calculate the total moles of acid in the 250 cm3 volumetric flask. Moles equals concentration times total volume. The moles of acid in the flask are 0.127 mol dm3 times 0.25 thousand dm3, which is 0.0318 moles. Propagate the uncertainty one last time. We add the percentage uncertainty of the acid concentration and the flask's volume. The total percentage uncertainty is 5.69% plus 0.1%, giving 5.81%. Converting this to an absolute uncertainty, we get plus 0.0185 moles. Step 6. Finally, we calculate the molar mass. Molar mass equals mass of acid divided by total moles of acid. The molar mass is 2.355 grams divided by 0.0318 moles, which is 74.06 ga-mole. And the percentage uncertainty in the molar mass is the percentage uncertainty in the mass of the acid, plus the percentage uncertainty in the moles of acid in the flask. This is 0.08% plus 5.81%, which is 5.89%. We can round this up to a single significant figure, 6%. The absolute uncertainty in the molar mass is 74.06 times 0.06, which is 4.44 gmol. Rounding to one significant figure, we get 4.4 gmol. So, the molar mass of the organic monoprotic acid is 74.1 plus or minus 4.4 grams per mole. This comprehensive example demonstrates the rigor required for HL calculations. Titrations are not always straightforward. For substances that are insoluble in water or volatile, a direct titration isn't feasible. In these cases, we use a back titration. In a back titration, we add a known excess of one reagent, A, to the substance we want to analyze, reagent B. We let the reaction go to completion. Then we determine the amount of the unreacted reagent A by a secondary titration with a standard solution. This gives us the moles of A that are left over. We subtract that from the initial moles of A to find out how much A actually reacted with the substance we're interested in, reagent B. A typical scenario is analyzing the amount of calcium carbonate in an antacid tablet. It's not very soluble, so we use a back titration. Let's work through this classic IB problem. An antacid tablet containing NaHCO3 is reacted with an excess of HCl. The unreacted HCl is then titrated with KOH. This problem involves two reactions, the antacid with the hydrochloric acid and the remaining acid with the potassium hydroxide. Here are the two balanced equations. The first shows the reaction we want to analyze. The second shows the reaction we actually measure. Our strategy is to work backwards from the second reaction. We'll use the KOH titration data to find the moles of excess HCl. First, we calculate the moles of KOH used in the titration. Moles equals concentration times volume. 0.200 mol dm3 times 355 dm3 is 0.0071 moles of KOH. From reaction 2, the mole ratio of HCl to KOH is 1 to 1. Therefore, the moles of excess HCl are 0.00071. Next, we need to know how many moles of HCl were added to the tablet initially. This is our moles of A before reaction. We calculate this using the initial concentration and volume of the HCl. 0.125 mol dm3 times 0.02500 dm3 is 0.03125 moles of HCl. Now we can find the moles of HCl that actually reacted with the antacid. This is the difference between the initial and the excess HCl. Subtracting the excess from the initial moles gives us 0.002415 moles of HCl that reacted with the NaHCO3. Looking at reaction 1, the mole ratio of NaHCO3 to HCl is also 1 to 1. So the moles of NaHCO3 that reacted are 0.02415. Our next step is to convert these moles of NaHCO3 to a mass. The molar mass of NaHCO3 is 84.01 gmol. Multiplying the moles by the molar mass gives 0.2029 grams of NaHCO3 in the tablet. The question asks for the percentage purity of the NaHCO3 in the tablet. We take the mass of NaHCO3 we found and divide it by the total mass of the tablet, multiplying by 100. Load 2029 grams divided by 0.300 grams times 100% gives a percentage purity of 67.6%. This shows how back titrations are essential for analyzing many types of real-world samples. Avogadro's law is a fundamental principle for gases. It states that equal volumes of all gases at the same temperature and pressure contain equal numbers of molecules. The volume of a gas is directly proportional to its amount in moles, which we can write as V is proportional to N. A direct consequence of this is Gay-Lussac's law of combining volumes, which states that for gases at constant temperature and pressure, the ratio of the volumes of gases consumed or produced in a chemical reaction is equal to the ratio of simple whole numbers. These numbers are just the stoichiometric coefficients from the balanced equation. This means that for gaseous reactions, we can substitute volumes for moles directly into the balanced equation. 1 volume of H2 plus 1 volume of Cl2 yields 2 volumes of HCl. Let's work through an example. Calculate the volume of air needed to burn 200 samLp3 of propane, C3H8. Air is approximately 20% oxygen by volume. First, write and balance the combustion equation. Propane plus oxygen yields carbon dioxide and water. The balanced equation tells us that 1 volume of propane reacts with 5 volumes of oxygen. This is a 1:5 ratio. Since we have 200 cm3 of propane, we need 5 times that volume in oxygen. 5 times 200 cm3 is 1,000 cm3 of oxygen. The question asks for the volume of air. Air is only 20% oxygen, so we need a much larger volume of air. If 1,000 cm3 of oxygen represents 20% of the total air volume, we divide 1,000 by 0.20 to find the total. This gives us 5,000 cm3 of air. So you can see how Avogadro's law simplifies calculations for gaseous reactions. Stoichiometry is an experimental technique used to measure the changes in the volume of gases during a chemical reaction. It's particularly useful for determining the molecular formula of gaseous compounds like hydrocarbons by analyzing their combustion products. Here's the general procedure. A known volume of a gaseous hydrocarbon is combusted in an excess of oxygen in a stoichiometer, which is a closed glass tube with a volume scale. The gaseous volumes are measured before the reaction and at several stages afterwards. After the reaction, the water produced is cooled to condense it into a liquid, so we don't count its volume as a gas. Any gaseous products are analyzed. We can remove carbon dioxide using a strong base like aqueous NaOH, and any remaining excess oxygen using a chemical like pyrogalol. The measurements of the gas volumes allow us to work out the number of carbon atoms and hydrogen atoms in the original hydrocarbon molecule. Let's work through an IB-style stoichiometry problem to find the molecular formula of an unknown hydrocarbon. Step 1. Write the generalized combustion equation for a hydrocarbon, CXHG. CXHG reacts with oxygen to form X moles of carbon dioxide and Y over 2 moles of water. We will use volume ratios from Avogadro's law to solve this. Step 2. Find the value of X, the number of carbon atoms. The volume of carbon dioxide produced is equal to the decrease in volume when NaOH is added. The volume goes from 80 cm3 down to 50 cm3. The volume of CO2 is 80 minus 50, which is 30 cm3. The volume ratio of hydrocarbon to CO2 is 1 to X. So X divided by 1 is 30 divided by 15, which is 2. The value of X is 2. Step 3. Find the value of Y, the number of hydrogen atoms. This requires finding the volume of oxygen used in the reaction. The initial volume of gas was 15 cm3 of hydrocarbon plus 95 cm3 of oxygen, making 110 cm3. The final volume after cooling was 80 cm3. So the change in volume is 110 minus 80, which is 30 cm3. This volume change is caused by two things: the hydrocarbon disappearing and the excess oxygen reacting with the produced carbon monoxide. A more reliable method is to directly use the stoichiometry. We have 15 cm3 of C2He. The reaction uses a volume of 15 times X plus 15 times Y4 of oxygen. Substituting X equals 2, this simplifies to 30 plus 3.75 Y. We know the moles of oxygen used is the initial moles minus the excess moles. Initial is 95 cm3. The excess is 50 minus 30, the CO2, so 20 cm3. This method is flawed, so let's use the reaction ratio. The text's final answer suggests the volume of oxygen used is 45 cm3. Let's reevaluate. Initial O2 was 95 cm3. The final residual gas after removing CO2 was 50 cm3, which must be the excess O2. So volume of O2 consumed is 95 minus 50, which is 45 cm3. Now we equate the volume of oxygen consumed with the stoichiometric expression we derived. We have 30 plus 3.75 I equals 45. Solving for Y, we get 3.75 I equals 15, so Y equals 4. With X equals 2 and Y equals 4, the molecular formula of the hydrocarbon is C2H4, which is ethene. This multi-step process, combining volumetric measurements with mole concepts, is a hallmark of IBHL chemistry. Thank you for watching this detailed tutorial. We've covered the essential aspects of stoichiometry and the mole concept for IB chemistry higher level. From calculating product masses to determining complex molecular formulas using advanced techniques like back titrations and stoichiometry, while also addressing error propagation. To solidify your understanding and excel in your exams, consistent practice is key. Now let's work through 5 practice questions together. Here is our first practice question. Take a moment to read it. Now let's look at the solution. First, we convert the masses to moles. For iron, 400 grams divided by 55.85 gives 0.0716 moles. For sulfur, 600 grams divided by 32.07 gives 0.187 moles. Next, we find the simplest ratio by dividing by the smallest value, 0.0716 moles. This gives us a ratio of 1 to approximately 2.6. To get whole numbers, we need to multiply the entire ratio by 3, which gives us 3 to 8. Therefore, the empirical formula is Fe3S8. Here is our second question. Calculate the mass of carbon dioxide produced from the combustion of 15.6 grams of benzene, C6H6, with excess oxygen. The first step, as always, is to write a balanced equation. The combustion of benzene yields carbon dioxide and water. Step 2, we convert the mass of benzene to moles. The molar mass of C6H6 is 6 times 12.01 plus 6 times 1.01, which is 78.12 GI-molecules. 15.6 grams divided by 78.12 grams per mole gives 0.200 moles of benzene. Step 3. Use the mole ratio from the balanced equation. 2 moles of benzene produce 12 moles of carbon dioxide. That's a 1 to 6 ratio. So 0.200 moles of benzene will produce 0.200 times 6, or 0.20 moles of carbon dioxide. Finally, step 4, convert moles of CO2 to mass. The molar mass of CO2 is 44.01 GI-mole. 120 moles times 44.01 grams per mole gives 52.8 grams. So 52.8 grams of carbon dioxide are produced. Our third question is a back titration problem. Practice question 3. An antacid tablet, 0.500 G/G, containing CaCO3 was dissolved in 20 100 at OCM3 of 0.200 mol DM3HCl. The resulting solution was titrated with 0.100 G/mol DM3NaOH, requiring 12.50 cm3 for neutralization. Calculate the percentage purity of KCO3 in the tablet. The relevant equations are the neutralization of the tablet with HCl and the neutralization of excess HCl with NaOH. Here are our 2 equations. First, we find the initial moles of HCl. Moles equals concentration times volume. On 200 times 0.02,000 is 0.0400 moles of HCl added. Next, we find the moles of excess HCl from the titration data. The moles of NaOH are 0.100 times 0.0125 which is 0.00125 moles. The mole ratio from EQ2 is 1 to 1, so moles of excess HCl are 0.0012. Now we find the moles of HCl that reacted with the KCO3 in the tablet. Subtracting the excess from the initial gives 0.00275 moles of HCl. From EQ1, the mole ratio of KCO3 to HCl is 1 to 2. So the moles of KCO3 are 0.0275 divided by 2, which is 0.01375 moles. We convert these moles of KCO3 to mass. The molar mass of KCO3 is 100.09 gr/mole. The mass is 0.01375 moles times 100.09 joules/mole, which is 0.1376 gram/mole. Finally, we calculate the percentage purity. Mass of pure KCO3 divided by total tablet mass multiplied by 100 gives 27.5% purity. This is a typical value for a chewable antacid tablet. We will now tackle our fourth question, which involves a dilution. A sample of concentrated sulfuric acid is diluted and then titrated with sodium hydroxide. We need to find the concentration of the original concentrated acid. The balanced equation for the titration is H2SO4 plus 2NaOH yields Na2SO4 plus 2H2. Note the 1 to 2 mole ratio. First, we find the moles of NaOH used in the titration. Moles equals concentration times volume. 1 mol DM3 times 0.2500 DM3 is 0.02500 moles of NaOH. Step 3. We use the mole ratio from the balanced equation to find the moles of sulfuric acid in the 20 100 cm3 sample. The ratio is 1 to 2, so the moles of acid are 0.02500 divided by 2, which is 0.01252 moles. Step 4. Calculate the concentration of the diluted sulfuric acid. Concentration equals moles divided by volume. 0.01250 moles divided by 0.0222000 dm3 gives a concentration of 0.625 mole dm3 for the diluted acid. Now we address the dilution. The initial 50 stoichiometry sample of concentrated acid was diluted to 1 dm3. The dilution factor is the final volume divided by the initial volume, which is 1000 divided by phi or 20. This means the concentration of the original acid was 20 times greater than the diluted acid. Step 6. Calculate the concentration of the concentrated acid. We multiply the diluted concentration by the dilution factor. 0.625 times 20 gives our final answer, 12.5 mole dm3. Here is our fifth and final practice question, which combines several concepts we've learned. First, we'll determine the value of N. The mass of water lost is the initial mass minus the mass of the anhydrous salt, which is 0.678 grams. Step 2. Convert both the anhydrous salt and the water to moles. The molar mass of FeSO4 is 151.92 g/mol. This gives 0.00541 moles. The molar mass of water is 18.02 g/mol, giving 0.0376 moles. Step 3. Find the value of N by dividing the moles of water by the moles of FeSO4. 0.0376 divided by 0.0541 is approximately 6.95, which we can round to the whole number 7. So N equals 7, and the hydrated salt is FeSO4.7H2O. Next, we need to calculate the percentage purity of the original sample. The question states the initial 1.50 gram sample was impure. This means not all of it was FeSO4.7H2O. The heating process would only remove the water of hydration, leaving the anhydrous salt and any insoluble impurities. The fact that the sample loses the expected amount of water and its mass becomes constant at the mass of the anhydrous salt, 0.8222 g, and that the total mass of pure hydrated salt adds up to the original sample mass, 11.5 g, indicates that the original sample was pure hydrated iron 2 sulfate. Therefore, the percentage purity is 100%. We hope this comprehensive review has been beneficial for your IBHL chemistry studies. We have covered a broad range of essential topics from the mole concept to titrations and eudiometry. Mastering these calculations and the underlying principles is crucial for success. The key takeaways are to always start with a balanced equation. Use the mole concept to relate different substances and practice applying these techniques to varied problems. If you or your friends need further assistance, DAR Tutors offers expert personalized tuition for IB, A-Level, and IGCSE chemistry and other subjects. Contact us to schedule a session and take your learning to the next level. Thank you for watching.